Okay, so I need to actually start covering the topic that listed for today, which is Gauss's law. So unless you have taken college level physics before, this will now be a new topic for almost everyone. I just can imagine this being covered in high school physics. For one good reason, let me write it down and you will see why. So this is what Gauss's law says. So Gauss's law it's a so Gauss's law, this is what it says. It says, so you calculate this quantity that's defined as electric field multiplied to some area. All right, you're multiplying area with electric field for some reason. And when you multiply this, you do it carefully because electric field, it's a vector, right? Yes? And you can just ignore the direction of a vector willy-nilly. And for the area, do you have a sense that area can be directed? Like this area versus this area. Are they the same or are they different? They're same amount of area, same magnitude, but would you say surface that looks like this for all purposes is exactly like surface like this? Like you wouldn't say that, right? There's a sense of direction to area. So we're going to start defining the sense of direction. Let me ask you this question. If you wanted to associate a single vector with the direction of a plane, how would you do it? Let me tell you what it cannot be. It cannot be any of the vectors within the plane because there's just so many. It's not going to be a single vector. Perpendicular. I feel like we talked about this in physics 4a, right? Yes, with the cross product? Yes? Yeah. So you associate a normal vector to this area, and you say that's the area as a vector. So area is a vector. It's not scalar. So let me indicate that information here. So we are going to multiply electric field to the area. And we are going to adding this up, and the surface that we are going to be considering, it's a funny looking surface, like, surface of a balloon. So it's not necessarily going to be a, Cartesian plane or whatever. So that means we have to start doing some calculus. And this is the reason I don't think you would have seen this in the proper form in the high school physics. So electric field times an infinitesimal amount of area. And I'm going to add it all up. So that's the integral. And I'm going to add this weird symbol. That's always going to be there. It has to be there. And I'll explain it in a bit. There's a circle that's overlaid on top of the integral symbol. Anyone have seen this symbol before? Other than to indicate section of a textbook. No one has seen it? Okay, we'll go over that. Or I guess we should talk about it now. So what this is indicating is that this is an integral over a closed surface. Does everyone here know the distinction between closed and open surface? So this balloon is an example of closed surface. It's clear how it's closed, right? Now, if I open up this mouth, then it'll become an open surface. There's a mathematical way to represent in what sense is this surface more open. We talk about it with the boundaries. So this balloon here, it's bounded by this circle here, right? And the fact that it has this boundary makes it not a closed surface. So if it has, when this boundary is gone, that's when it's a closed surface. So, but I think most people have a good sense of what is closed surface and what's not. So a closed surface would also enclose a volume. There would be like a volume of a sphere or some volume that would be enclosing. So you can already see Gauss's law. There's a reason many of you, how many here have heard of Gauss's law before this class? Well, some of you, okay. But there's a reason most people don't hear about this, because even to state the law requires you to know calculus. requires to know some mathematics. That's why you wouldn't have heard it, most of you wouldn't have heard it outside of college or university physics class. So this strange quantity, when you're done computing all this, Gauss's law says this. It says this quantity is equal to amount of charge enclosed divided by some constant, epsilon naught. The electric constant that I've been using when I was plugging in numbers in class before. So this is the statement of Gauss's law. It takes a while for this to full implications and applications of this law to sink in. And that's really what your lab section after this evening is about. I'm just setting aside 2 to 3 hours of time so that you can do nothing but going over questions that relate to conceptual issues in applying Gauss's law, starting back from electric fields, field lines, and electric flux. So you're going to have 2 to 3 hours in the lab today to do all of that. I don't expect me lecturing 20 minutes right now will really help you a lot in understanding this. So for right now, let me use this time to define some terms and do one quick example so that you feel like you have some starting point when you come back for lab. Good. Okay. So let me define a new term. So there's this term that you are going to start seeing a lot. It's a term called flux, something called a flux. Right now we are talking about electric flux. Later on, we are going to talk about magnetic flux when we talk about magnetic fields and whatnot. And with the flux, we usually use the symbol phi. So if you're talking about electric flux, it would be phi sub E. And in fact, this quantity here, this you could call it net flux out of closed volume. So the way flux is defined is it's defined this way. Flux is defined as electric field as a vector times area as a vector. And because it's two vectors multiplying, you have to tell people, is it going to be a cross product or a dot product? Well, it's a dot product. So flux tells you, so flux is a scalar amount that's given by electric field, dot product with area. And that's what this is, except you're doing it over very specific type of surface. If you're just talking about flux in general, you can talk about flux through any kind of thing. So, for example, I guess I can use this example here. Let's say I have set electric field set up like this. And so if I have an area here that's set up inside this place where there's a lot of there's electric fields, then to calculate the amount of flux, you would just plug numbers into this formula. See what the strength of electric field is over this surface, multiply by the amount of the surface, and if you are being careful with this dot product here, it's the magnitude of electric field times the area of the electric field, and what else? Area of the surface, and there's one more thing to express this dot product. Cosine of angle. What angle? How are we defining that angle? Well, vectorial, it's angle between E and A, right? So here, it would be the angle between the E that's drawn here and the vector direction for the A. So when this surface is oriented this way, the flux is like a maximum because theta angle here is 0. And as I turn this surface, the flux decreases. At what orientation would I have minimum flux, as in minimum magnitude of flux? When it's parallel, right? So So while trying to be careful not to give you a wrong impression, here's a mathematical analogy that works well for flux. So once again, I'm going to keep saying this caveat so that you don't misunderstand. These electric fields, when you draw them, it looks like something's flowing from left to right, right? Now, to be careful, nothing's actually flowing. We're just saying this is the electric field. Nothing's actually moving from left to right. But there's a reason the people chose the phrase flux to describe this quantity. Because if you imagine this like a flow, then this quantity E dot A here, it describes how much is flowing through this area. So that when this is turned at some angle, like this, nothing is flowing through the area, so you get 0. When it's turned this way, you get most amount of flowing through the area as represented by theta equal to 0. So that's the definition of flux and some intuition about the flux. Which means, let me do this, so let me use illustrate Gauss's law to the simplest possible situation. Simplest possible charge distribution, which can be producing electric field. So somebody suggests, what do you think is what's the simplest charge distribution you can imagine? Like, I mean, the simplest would be, having no charge at all. That's what's called a trivial solution. So something that's non-trivial, something where there is actually charge. Which of these scenarios that you have seen seems to be simplest? Plane? Plane is actually not the simplest. Or you are looking at what the expression for the electric field is. But I mean, if you watch the actual video, you do not think a plane of charges is simple. It's not. Point charge, right? Point charge is literally, having this thing at one point. It's literally one charge. And that's what we started our description with, the Coulomb's law. So let me just do this example for point charge, and I think I may have more time to do some of rederivation of some of these examples. So let's just say I have a point charge. And to get a sense of this charge distribution, one of the first thing I'm going to do is I'm going to draw electric field lines around this charge, because that'll help me think about, all right, what does my picture look like? So let me draw my electric field lines here. So pointing away from the charge. I guess I'll draw 8. 4 looks a little bit weird. It's also numerologically bad. All right. So, well, not that that matters. That actually doesn't matter. The second thing. So this is my positive charge, and these are the electric field lines coming from it. All right, I promised that I would make use of Gauss's law or make some sense of it. All right, what's lacking in this picture? Something's missing. I have electric field, but something is missing here to make a sense of use of Gauss's law. Some closed surface, right? Now, so this is something that I want to clarify. There is something that we are going to refer to as Gaussian surface. Gaussian surface. And what I want to say now is that we are not referring to any physical surface. We are not talking about a literal balloon containing this charge. When we talk about Gaussian surface, what we are going to talk about is a surface that we are going to define. It's an imaginary surface. It doesn't actually exist, but we are going to say, well, I'm going to define a surface so that I can apply Gauss's law. Let me define a surface here. Let me be a little bit, unusual. And I'm going to define a cube that encloses this charge. So my surface would be the surface of this cube. Good? So now I have surfaces. So what you can maybe imagine doing is you can now imagine calculating the flux, electric flux of E times A through each one of these surfaces. There are 8 of them. Let's imagine doing flux calculation for one of them here. Do you imagine that would be an easy calculation? No, what would make this calculation? If I'm trying to calculate the flux through this surface, what would make it difficult? Like what consideration is making you say, oh, that doesn't sound easy?
Because there's like 3 dimensions. I mean, yeah.
Well, everything's going to be in 3 dimensions.
Oh, okay.
So if you're trying to calculate this, what gives you a pause as you're trying to calculate this over this one surface? Sungmin, anything give you a pause? If I simply ask you, okay, what is the flux here? Who knows the answer to that? Let's say, I give you what the amount of charge Q is, I give you the length of the cube, and I ask for the flux for one of the surfaces of the cube. Anybody know the answer right off the top of your head? Okay, let me ask this. So when you look at expression like this, the first thing you should ask is, okay, is there a value you can plug in? Is there a value you can plug in for area? Yes? L squared, right? Area of a cube. Okay, not that hard. Is there a value you can plug in for electric field? Now, you might say, let's say, I think this is where Sungmin might be going, I hope. So let me write it down. So you say, all right, I know the distance here. The distance here is L over 2. So you might say, oh, electric field of point charge. I say electric field is KQ over L over 2 squared. And I say, okay, flux, that's electric field times the area, L squared. What's wrong with that? There's actually something that's missing in that argument. Direction of the electric field? Well, I guess here it's pointing that way. So, area points also, I can say. Oh, so by the way, this is a convention about area. When you have a closed surface, the convention is that the positive direction for the area points outward. That's the convention that we use for a closed surface. So, okay, direction of electric field seems fine. There's one thing wrong with it. Yes? Oh, were you raising? Okay. So if if we went through this calculation and said my flux is equal to KQ times over, I guess, 4 times L squared times L squared, and say flux is equal to 4KQ, I would say, all right, that is wrong. And in fact, I think you can show that that's wrong when you try to reconcile it with the Gauss' law. I don't have time to do that, so I won't do that. But all this calculation, this is wrong. So what can I point to and say, yeah, that's not right. I made a mistake here. In the interest of time, let me tell you where the mistake is, and maybe one of you can tell me why that's a mistake. This is where the mistake is, using this value for electric field. What was wrong with it? Electric field at this point, that's what I did. So what are you getting at? Yeah. Electric field at different points of this surface will have different value of electric. At different points of the surface have different value of electric field. So when you look at this, the first question would have been, what value of electric field can I plug in? And if you know, understood that at different points, they're at different distance, so it's going to be different value, then it's going to be different direction, then your first thing would have been, I don't know what value of electric field to plug in. So if you are to do this calculation just using the definition of flux, it's going to be a long calculation. I'm not going to do it. There's a homework problem that's similar to this where you shouldn't really do it that way. The way you should do it is you should use Gauss's law. So here's something that Gauss's law actually does tell you. So Gauss's law won't tell you the electric flux through a single surface. But it'll tell you electric flux, the net electric flux over all 8 surfaces. Because if you're adding them all up, then now you have met the condition for the left-hand side of Gauss's law. That you have E dot dA added up over the entire closed surface. So what is the charge enclosed in this picture? What is the charge enclosed? I mean, it's a simple answer. Yeah, the Q that I enclosed, right? There's no other charge here. So here you can say the electric flux. So the total flux that's enclosed, which you could also say is, that symbol there, E dot dA, is equal to, well, what Gauss's law says it is, Q over epsilon naught. And so this tells you what Gauss's law means. It doesn't quite tell you how it's useful to you, right? Okay, so that's it. That's the value of flux. Why do I care about flux again? Like, why? So in the remaining 3 minutes or so, let me show you how you can use Gauss's law to actually derive electric field. So this is the reason we are introducing Gauss's law in this class. It's not so that we can calculate flux. The flux is how we state Gauss's law, but what we are secretly interested in is actually this quantity here, electric field. Then, when you look at it, you will realize, how am I going to get to electric field? It's inside an integral. It's a function of position. I can't just pull it out. So the way you apply Gauss's law to find the electric field is you exploit symmetries. And that's going to be one part of the set of exercises that you will go through. In the past semesters, I tried to teach it during lecture, and it never worked. I would say a bunch of stuff for like 30 minutes, and no one would understand a single thing about symmetry. I think you really have to go through the exercise yourself to get it. That's why I'm setting aside 2 to 3 hours during lab for you to do it. So let me go through this quickly. I have only 2 minutes left. So I have charge of plus Q here. So I have electric fields that look like this. And this is what we mean by exploiting symmetry. So there's some particular symmetry that this distribution of charge is obeying. In the interest of time, I'll just say it. It's a spherical symmetry. As in, if you are out at a point here, if you're out at some point at distance r, then you have some magnitude of electric field here, right? Let's say you moved to some other point that's also at distance r. Will I have the same electric field strength? Yeah, and we actually do not have to refer to Coulomb's law. I actually am not going to. The way you do it is you imagine taking this, and you imagine rotating the whole situation by 45 degrees. When you've done that, you take the charge, rotate it by 45 degrees, you haven't changed anything. So that's the argument that says these electric field magnitudes have to be the same. Imagine finding all the points that are at distance r from this charge. What would those set of points build up? Sphere. So that should be the Gaussian surface that we define if we are trying to find the electric field with it. So I define a spherical, sorry, I'm not drawing the sphere well. If you define a spherical surface, spherical Gaussian surface around the charge, then this is what you know. You know that on the surface, electric field is constant from symmetry. And knowing that allows you to do something amazing. So you write down Gauss's law, which says, let me write it down here. You write down Gauss's law, E dot dA, and you look at the relative direction of the dA and the electric field, which is also pointing outward. So this E dot dA, that's going to be just the magnitude E times the area dA. Good? And we said the electric field is constant, uniform. So what I think I would like to do is I think I'm going to want to pull it outside the integral. Am I allowed to do that? Yeah. Over the surface I'm integrating, this doesn't change. It's a constant. I can pull constant out of integral. So this becomes closed surface integral around the dA. Anybody know what this should be for a sphere? Or if you don't know the formula, describe what it should be. 4 pi r squared, or the surface area of a sphere. So this is simply going to be surface area of the sphere, 4 pi radius, I guess, lowercase r squared. So this is the left-hand side of Gauss's law. Electric field times 4 pi r squared. We have gotten electric field outside the integral, and we have done the integral. The right-hand side of the Gauss's law, Q enclosed over epsilon naught, that becomes plus Q over epsilon naught. Let me solve this for electric field. When I do that, this is what I get. Solving this for electric field, I end up with E is equal to Q over 4 pi epsilon naught times r squared. Does this look like anything you have seen before? Sure, I'm out of time, but I can wrap this up in 1 minute. E is equal to Q over 4 pi epsilon naught. I guess this is the important part, r squared. Does that remind you of anything you have seen before? Any other expression for electric field that goes as 1 over distance squared? Well, yeah, the Coulomb's law. So this is why Gauss's law is the fundamental law. We can derive Coulomb's law from Gauss's law. So we don't actually need the Coulomb's law. Once you have a sense for electric field, and you have all that intuition, then we can just start from Gauss's law. This is the basic law of electrostatics. And really this is the reason I wanted to wrap this up here. The fact that you get 4 pi here, the fact that you get this here, this is the reason for the constant k that we have been using. This is the reason for k being equal to 1 over 4 pi epsilon naught. So the 4 pi you see here, it's not really arbitrary. The choice, when people were defining these units, the choice was made to have 4 pi here so that you would not need 4 pi anywhere here. So SI unit is the system of units that made a choice to make Gauss's law look as simple as possible. And doing that meant, your Coulomb's law would have this weird factor of 4 pi in there, but that's fine because Gauss's law is the fundamental law. That's what we want to look simple, not Coulomb's law.